Good morning and welcome back. We're going to start this session with a discussion on digital systems and software and how they have had an impact on how we define quality. We're also going to touch on what makes them so unique and how they affect operators. We're going to offer some examples and at the end conclude with some key implications and takeaways. Now, if we were to approach consumers, customers, and ask them if it's okay for a manufacturer to ship them a product that the manufacturer knows is defective, and they just try to fix it later after they get it home, most of us, would say no. Get the product working right and then sell it. And that has been the general direction and mantra, if you will, of quality throughout the 20th century. But then things began to change in the 1980s and early 90s when people started buying computers, and manufacturers quickly realized that they didn't want those customers to take the computers back every time there was a bug in the software or firmware that make the computer work, and then have the technicians or the manufacturers themselves update the computer. Instead, they started publishing what today we call patches. They would take fixes, post them on an FTP site. The customers could then go in, download the software or the firmware, update their computers themselves, and voila, everything is working. Now, that was fine for computers and later on for game systems. The problem is that software didn't just stay with computers and game systems. Today, software and microprocessors and the firmware that run them are ubiquitous. They're everywhere. You can buy almost any machine without it having at least a control system run by software, and frequently they'll have microprocessors inside the machine themselves. In fact, we have microprocessors today in microwaves, refrigerators, almost anything of significance that we have around the house. So over time, this attitude that you can ship things first and fix them later escaped the confines of computers and gaming systems and got into areas with real safety significance, including cars, power plants, airplanes, medical equipment, and so on. And that is the key challenge we face today. All right, so once manufacturers became comfortable with the notion that they could build a system that had known bugs in them and actually fix them after they deliver them to the customer, that process, which was so different from the way that quality was viewed before, began affecting the culture of the development teams, at least on the software side. But it also affected manufacturers in terms of defining just what is good enough to ship. Now, frankly, had it stayed with computers and gaming systems, we wouldn't be having this conversation. But digital control systems, digital systems in general, quickly migrated into all kinds of areas with real safety significance, including controlling power plants, flying airplanes, driving cars, running medical equipment. Each of these is different from those computers and those gaming systems because there are lives at stake. Let me offer you a couple of examples. The first was a Peruvian aircraft that some years ago ran into some problems at night. And the crew decided that it wanted to turn around and go back and land and fix the problem. It was a safety issue. But flying at night, they couldn't really tell what their altitude was. And part of the problem they were facing had to do with the instruments that were telling them how high they were flying. So they struggled trying to get the plane back and land it safely. And at one point, they actually called the air controllers and asked them how high they were flying. They wanted to know their altitude as validated by the air controller. And the air controller gave him a number that turned out to match the number in the cockpit. Unfortunately, the reason that happened was because on the air control system display, that altimeter value came from the airplane through a transponder on the tail. In other words, the airplane was saying to air traffic control, I am flying at this speed in this direction and at this altitude. It was not an independent measure. So what happened in practice was that the air controller validated wrong information, which convinced the pilots that they were flying higher than they actually were. They started getting the plane to descend and ultimately realized what was going on when the left wing, I believe it was, hit the water. They did manage to recover the airplane and regain control, but that only lasted for a few minutes, and ultimately the plane went into the water and killed everybody on board. In 2009, an airline flight from Rio to Paris, flight 447, ran into similar problems when a pitot tube either got plugged or failed. And as a result of that, the flight management system was getting erratic airspeed indication. It tried to deal with the situation. It was putting out alarms that actually started confusing the crew. Ultimately, it could not reconcile the conflicting readings, and it simply turned control of the airplane back to the pilots. So these guys, who have been basically in caretaker mode, because these planes basically fly themselves, suddenly had to snap to attention and start making decisions. Well, they got confused. And it's tragic to read the transcripts from the cockpit voice recorder, because they demonstrate how quickly they got confused, and then they stayed confused. And that confusion led to a series of poor decisions that ended when the plane hit the water and killed everybody on board. Now, this has happened with automobiles, this has happened with power plants, it has happened in a whole range of applications. And there are real implications then for operators, pilots, others who run these systems, run these plants. If you're an operator, one of the things you have to be careful with is that software, these digital systems, can paint an image of reality that can capture your attention. And we know from history, from accidents, that this can be a deadly trap. So what to do? What I tell operators is that they need to keep three things in mind. One is the reason they are where they are. There's a reason why we put pilots in cockpits, why we put operators in power plants, why we put operational support engineers in power plants, and we used to have them on airplanes. And that is, at the end of the day, no matter how automated, judgment lies with a human being. So it's critical for every operator to keep that in mind. Associated with that is the need to keep a little bit of skepticism when we look at control systems, at displays. Again, we know that these displays can have a compelling impact on operators. So one way to deal with it is to remind ourselves that what we're looking at is not reality, and it could be wrong. Keep your skepticism. Third is to maintain situational awareness. One of the problems with these automated systems is that once engaged, they leave operators with nothing to do. They can sit back, they can read a book. They have had pilots who were trying to take tests while the airplanes were flying themselves. They didn't have anything to do. They had their laptops, so they were training and taking tests. They weren't supposed to, but they were doing it. Now think about it. You're relaxed, your mind is on other things, and all of a sudden something happens. And the flight management system says, hey, I can't figure this out. I'm out of here. It's all yours. That's what situational awareness is very critical. Because you have to be able to look at the reality in front of you. what that computer screen is telling you and say, you know, that doesn't feel right. Now, here's the thing. Most systems today have different sources of information. For example, aircraft include other systems other than one side pitot tube or the other side pitot tube. These are independent. And the pilots can switch back and forth. That can tell the aircrew the airplane's airspeed. So they have the ability to compare the two. Pilots can tell what power level the engines are at. They can see how the plane has been configured. So there's other ways that they have of telling what is going on with that airframe. But in order to do that, they have to maintain situational awareness, a touch of skepticism, and they have to remind themselves that they are pilots, that they should be able to fly that airplane even if all of those displays went dark. And those are the key takeaways. Number one, you're an operator, you're an engineer, you're there for a reason. Number two, just because a screen is painting a picture for you doesn't mean that that picture is right. Number three, maintain your situational awareness so that if it turns out that the picture being painted for you is wrong, or if the control system becomes confused or overwhelmed and turns the system over to you, you can immediately step into his shoes and start running it yourself. Those three key principles would have saved hundreds of lives in a number of different accidents. So keep them in mind in your profession as a pilot or operator. We'll get back here in a few minutes and pick up with the exercises.